Hello, we are Santiago, Cesar, Ashley, and me, and we're going to present our evidence number two. This presentation will be divided in the following sections: introduction, phantom design and construction, phantom evaluation, algorithm implementation, results, general conclusions, and finally, references. Phantoms have two main uses: the clinical one, where it is used to help train clinicians to identify vascular diseases such as an aneurysm or stenosis in an artery in a safe and repeatable setting. The other one is the educational one, where in medical schools and labs it is commonly used to teach anatomy and sonography. The imaging modes used on a phantom are the B mode for analyzing structure and Doppler to analyze flow. The purpose of this project was to build and test a vascular phantom classifying images with a neural network. And it was a team-based task to create a phantom with a 50 to 80% of stenosis. We decided to make our phantom in a plastic topper with plastic tubes to simulate the artery. For the tissue, we prepared a mixture of agar-agar, glycerol, and citric acid. These materials were selected because of the desired biocompatibility and ecogenicity of the phantom, as well as the low cost. The dimensions of our phantom were 290 times 205 times 80 millimeters, and on the lateral faces, we drilled three holes: one for the aneurysm artery, one for the normal artery, and the other one for the stenosis. Each hole was 13 millimeters wide, and they both had a separation of 60 millimeters.
This is the process. The agar mixture was prepared by making 5 liters of the mixture, including 5% of agar-agar, 10% of glycerin, and 0.5 of citric acid, and the rest of water. Then it was mixed cold to avoid lumps and raised to a temperature above 90 degrees to achieve proper polymerization. Finally, the mixture was allowed to polymerize at room temperature for 8 hours. To create the stenosis tubing, a segment was heated with the help of a bar to apply external pressure and achieve a smaller diameter. And the pump we use in this model with a maximum flow of 5 liters per minute. This is the evaluation, and what we can observe in the following image is that the first is a color Doppler image, which means that flow is circulating in the artery. But in this case, different colors are observed, indicating that the flow passing through that section is turbulent and multidirectional. However, in the image 2, there is no flow, it's only the artery in B mode brightness, so we only see a healthy artery. And in the third, the same healthy artery can we observe in a Doppler mode, and we can see that the flow is laminar, unidirectional, and doesn't change colors. In the following images, the artery can be seen with stenosis at different flow rates. We had three types: high, medium, and low, and the difference in colors and intensity indicates that the changes are visible. In the table, we can see the voltages for each flow rate and estimate of the flow rate, taking into account that our pump has a maximum of 12 watts.
So, about our neural network, our model was fully implemented from scratch in Python without relying on high level machine learning libraries like PyTorch or TensorFlow. The neural network has a simple two layer architecture. The input layer corresponds to the pixels of each DICOM image that were resized by 128 by 128 pixels. Then we have the hidden layer that contains 10 units and uses the ReLU activation function. Finally, the output layer has one unit, as it is a binary classification between healthy versus stenosis, and it uses sigmoid activation to produce a probability between 0 and 1. The model performs very well for both normal and stenosis. It detects all normal cases and only misclassified one stenosis case as normal. With an overall accuracy of 92%, it demonstrates strong classification capabilities, especially with given the small dataset and the quality of this dataset. We split into training and validation sets of 80-20. The tests were made only in 12 images. The first graph showed the loss versus epochs, where we observe a steady and consistent decrease in loss from around 1.4 down to below zero point 0.2, indicating that the model learned efficiently. The second graph illustrated decision boundaries in a 2D space after applying a PCA for dimensionality reduction. The reds and blue dots represented two target classes, and the background showed how the model spread them. The boundary effectively distinguished the classes with only a few misclassified points. These results align with our classification report, which showed a high overall accuracy of 92%, strong F1 scores for both classes, and a good balance between precision and recall. In summary, the model demonstrates robust learning, effective decision boundaries, and high performance in classifying the data. Using a simple Scratch function to test prediction, we can see these two examples where the model classified in a good way. From the first image, we can see that it's a healthy basal and the model predicts healthy. And the other one is with stenosis and the model predicts stenosis.
The agar plus literal mixture demonstrated excellent echogenicity, producing high contrast beam-mode ultrasound images suitable for anatomical simulation. The phantom structure yield realistic vessel morphology, enabling clear visualization of a simulated stenosis, with visible narrowing and signal variation. Due to its low cost and good performance, this phantom is ideal for teaching purposes and used in low-resource clinical settings. The relationship between material composition and image quality highlights the importance of realistic acoustic properties for effective clinical training tools. The proposed CNN showed promising results in distinguishing normal from stenosis vessels, with high classification reliability on acquired data. The phantoms successfully stimulated vascular stenosis, producing high-quality ultrasound images and enabling consistent detection through image analysis and classification. The low-cost, easy-to-manufacture phantom proved suitable for biomedical education, hands-on ultrasound training, and preliminary clinical simulation tasks. The implemented CNN model demonstrates reliable classification between normal and stenosis vessels, confirming its potential for computer-aided diagnosis when trained with critical data. We recommend refining the phantom's internal geometry, exploring new biomimetic materials, and expanding the dataset to improve AI model generalization and simulation realism.